All right, let's get started. Today we're going to start talking about recurrent neural networks. I will define what they are, show you a bunch of different variations, and hopefully we'll have some time to run through some notebooks together so you see the actual code that are used for these types of neural networks. First, what are these neural networks, recurrent neural networks, good for? They're usually used in sequence-related problems, especially on the natural language processing side. They're very popular because the text can be seen as a sequence of words or sequence of characters. There's many sequence-related problems that we can give as examples. Sequence classification is one example where we read an article and then we classify the sentiment in that article. That's a type of sequence classification. Sequence generation is an example if you want to look at a picture and then generate a natural language sentence. That could be seen as a sequence generation problem. Sequence tagging, so you have an input a bunch of words, and as output you want to generate the part of speech, meaning noun, adjective, adverb, etc. for each word in the sentence. So that's a sequence tagging problem. There is also sequence-to-sequence models where the input to the model is a sequence, the output is also a sequence, not necessarily aligned element-wise. And a typical example of that is machine translation. So you have an English sentence coming in, a Turkish sentence coming out. The Turkish sentence is usually much shorter than the English sentence in terms of word count, and the words are not necessarily aligned one-to-one. So we'll look at some architectures to deal with that problem. Now, the common property of all of these problems is that the input and sometimes the output is of variable size. So far, for both CNNs and MLPs and linear models that we've seen, the input was always a fixed size. So, for example, an MNIST image is a 28 by 28 input. But if you're processing sentences, some of them are going to be 5 words, some of them are going to be 50 words. So we have to find a way to deal with variable sized inputs. So let's do some brainstorming together. And as an example, I'm going to use the sequence tagging problem. So in sequence tagging, we basically have an input sequence, x1 through xn. And I want to assign some classes to each token. Let's say part of speech was the example I used, y1, y2, yn. So that's my input sequence, that's my output sequence. And one thing we can do is, for example, we can use a multi-layer perceptron to turn the different x's into y's. So each of these boxes represents the same multi-layer perceptron classifier. Okay. Now, this would certainly do something, but it wouldn't actually perform very well because MLP has no memory, no history of what has come before. Right? So presumably, if x1 through xn is the words of a sentence, and y1 through yn is the noun, verb, adjective, etc. that go with these words, these things are sort of the elements of the sequence are not independent. Right? The words that follow each other are usually predictable, they're dependent. Also, the parts of speech, the y's are interdependent as well. So, for example, if you see a determiner like a or the next word is probably an adjective or a noun. So there's dependencies involved at various time steps that this model is ignoring. And we'd like to create a model that takes into account those dependencies. Now, all of the models seen until now, MLP and CNN included, take one input, generate one output, and then forget everything. So when you see the next input, you start from scratch, right? So you don't remember anything about the previous examples that you have processed. And that works fine if all the input-output pairs in your data are independent of each other. Then you don't need to remember anything. But in these sequence cases, that's no longer true. So one thing we can do in order to solve this problem is, well, since the input is a sequence, why am I taking the input one token at a time? So let's take this as a sequence. So let this be my whole input, and let this be my output, and let me train some sort of model, MLP, whatever, that takes the whole sequence as input and generates the whole sequence as output. Right? So that way it can take into account any type of dependency between the different x's, it can take into account any type of dependency between the y's. So what are some of the problems you can foresee with this architecture? Yeah?
There are variable sizes, like
Right, so that's one of the problems. So presumably, let's say x1 through xn are words, or more precisely, I'm going to represent each word with a vector of a certain size. And so if I, to represent the sequence x1 through xn, I'm going to concatenate all these sequences together, and to have an, if individual words are d-dimensional, then the whole sequence is going to be n times d-dimensional. So my input size is going to be n times d, and then my output size is going to be n times some other dimension for y's, n times c, let's say. But n is changing, right? So for one input, n, the number of words is going to be 5. For another input, it's going to be 50. Our MLP models or CNN models typically cannot deal with inputs of changing size. So what else do you see as a problem? Number of parameters is under our control, right? So if we have a linear model, for example, there is no hidden layers, so it's just basically the input dimensions times the output dimensions is the number of parameters. And also these individual word vectors or class vectors are also in my control. I can make them 16 dimensions per word or 100 dimensions per word. That's also under my control. But yes, in order to learn this thing effectively, you may need a very big model and have a lot of parameters. That's true. What else? Yeah?
There are possibly, as you said, dependencies between inputs and outputs.
Mm-hmm.
However, it is not a global dependency, right? It might be a problem maybe.
What do you mean by global dependency?
Yeah, I mean like x1 is not dependent on xn actually.
Maybe it is, maybe it's not. In Turkish, if f1 is the subject and xn is the verb, they're definitely dependent on each other because verb is a marker that's
Is this a
indicating what the
sentence
subject
or
is.
a big paragraph?
Is the sentence.
Then it might be, yeah.
Even in a big paragraph, the first sentence definitely has some effect on the last sentence. They need to be about the same topic.
Yeah, in topic-wise maybe.
That's a dependency, right? So you can't independently generate a first sentence and a last sentence of a paragraph. So there's always dependencies.
Problem, okay. Because how much dependency is there? Like maybe there is a mathematical.
So maybe you're saying the input tokens that are far away from each other are less dependent. So I'm wasting a lot of resources trying to connect everything to everything.
Yeah, kind of.
Whereas in the first model, I wasn't connecting anything to anything. That's also not a good. Maybe there is a middle ground, which I will come to that in the next
Maybe
one.
there is a pattern between, we continue sentence by sentence, and we have x1 to xn in one sentence. But when we go to the next sentence, we may encounter the same pattern, this xy, xi, yi here.
Okay. And if we do, what's the problem?
Dependency between sentences.
Oh, I see. So in this case, we're forgetting the whole sentence by the time we get to the next sentence, and maybe the previous sentence had some clues about this sentence as well. Yes, that's a possibility.
Why do you forget the weights will update after that sentence?
I'm thinking about test time. During test time, basically there is no dependencies between the two sentences. So what you're saying is also true for any MLP or CNN that's during, doing some training. Obviously, one batch updates the weights, and then you look at the next batch with those weights. I'm not talking about that kind of dependency. I'm talking about, given a fixed model, do I actually remember anything from one thing to the next? One problem I'd like to point out is that this is not quite a classification problem, and it's not quite a regression problem. Remember that when we first introduced different types of supervised machine learning, we said if your output is categorical, like digits 0 through 9, like MNIST, that's a classification problem, and we have softmax for that. If your output is numerical, one or more numbers you're generating, then it's a regression problem, and we use the quadratic loss function for that. Here, the output is huge. So the number of, if we actually look at each distinct output as a different category, the number of categories is exponentially large, right? So if each yi can take one of 10 possible values, and this sentence has 50 words, then your output space is 10 to the 50. So you need to actually learn parameters, whatever you need, for 10 to the 50 different possible output categories. Okay? So it's actually not correct to call these things categories anymore. The output has structure, the output has pieces, and these pieces have dependencies on each other. And this is called a structured prediction problem. So it's neither classification nor regression. You have a discrete output space, but it's huge. It consists of pieces, but these pieces cannot be independently generated. So we call this a structured prediction problem. So that's another problem with this approach. If I use this approach, I will probably never see the same y ever again. Okay? So each sentence is going to have a different sequence of part of speech labels, which means I will have a training set where the same answer never repeats twice. How can I learn anything if I don't see the same answer more than once? Right? Yeah, question?
Is this similar to time series for models?
Any sequence is similar to any other sequence. Time series is a sequence, financial data is a sequence, DNA data is a sequence, language is a sequence. These are all sequence problems. Time series analysis are basically very sort of simple and early attempts to model sequences, and the types of RNNs we're going to see are a lot more sophisticated than, they can represent a lot richer set of functions than the typical time series methods. Yeah.
So if we were to, let's assume the output is a d by n vector, would we circumvent the problem like you told about if we split it into n d times 1 vectors and then...
Right. So I'm going to actually try something like that. So combining your idea with this idea of maybe we don't need that much dependency. So I'm going to suggest something like, go away. So what we can do, and what people have done, x3 dot this one xn, and so for example, let's talk about y2. y2 is the label for x2, right? And presumably it's influenced more by x2 itself and its immediate neighbors than the words all the way at the end of the sentence. So I'm going to assume, let's say, the immediate neighbors of x2 are going to be my inputs, and I'm going to predict y2 looking at a window of inputs centered at x2. Okay? So that means for every, so for example for yn minus 1, I'm going to pick a window that's centered on xn minus 1 and its immediate neighbors. Now, I took a window size of 3 here, but you could also take a larger window size depending on the application. Okay, so this is the this solves a bunch of problems at once. One, that my inputs are no longer variable size. I always have 3 inputs. Okay, so I can use an MLP, it's a fixed size input. 2, I'm predicting these labels one by one. So now, every time I'm predicting, it's a real classification problem. It doesn't have this huge exponential space, because each yi is predicted independently. So those problems are solved. However, and this is the early attempts at building language models or taggers using neural networks, looked like this. The drawback of this is that you never know what size window is enough, and no matter what size window you choose, there are cases where information outside that window actually is beneficial to your prediction. Yeah, that's all I'm going to say. It's an inelegant solution. So a more elegant way to solve this problem is basically the RNN way. In all of these cases, we had sort of y hat t, maybe except the second one, is a function of some xt input in the first solution, let's say, and some parameters, right? So this was the description of the first model, for example. In the second model, the whole y hat sequence is dependent on x sequence and w, and in the third model, y hat t also depends on xt minus 1 and xt plus 1. But basically, there is always the input or a subset of the input plus the weights passed through some function that give you the output. Now I'm going to draw an RNN. And it's going to look very similar to the first picture, with one crucial difference. Okay, so far I have the first model. Now I'm going to add something. So these are sort of a secondary output. So basically, instead of having a single input and a single output, I'm imagining a network, a MLP-like model that has 2 inputs and 2 outputs. In other words, if I call these hidden outputs HT, so let's call this H1, for example, then I'm going to output both my Y prediction and the next hidden state I'm passing forward as a function of the current input, the weights, my MLP weights, and the previous hidden state. Okay? So if you compare this with that, or the first picture with the last picture, the big difference is I basically added an H variable both to my input and to my output. This H variable is going to act as my memory. Whatever I need to remember about this problem from one time step to the next, hopefully it's going to get stored in this H variable. So the H variable is going to carry the dependencies forward. Okay? So that's the big idea of RNNs.
Do I define a function for H?
H is going to be one of the outputs of my model. So for example, let's see if I can show you an example. So here it is in code. Okay, so a simple MLP versus a simple RNN. What's the difference? Let's see. So in the MLP, I have some parameters and input, right? So the hidden layer is computed by, you know, applying some linear function to the input and then taking a nonlinear transformation of the result. In this case, I'm using tan h, for example, instead of relu. Okay? And then the output is a linear function of the hidden state. So this is a one hidden layer MLP that we're familiar with. The only difference is the multiplication. I usually do W1 times X. Here I did X times W1 for reasons of efficiency that will become clear later. But you can do it either way. Any questions about MLP1? Okay, so that's something you're familiar with. Here's RNM1. In addition to parameters and input, I also take this vector called hidden. That's the only difference in the input. Then I concatenate my input and hidden together, make one big vector, consists of my x and h variables. I apply the exact same transformation to that input, which I call input 2 now. And I compute the output the same way. And this is the final difference. When I'm returning my result, I return the final state of my hidden as well as the output. Okay? So this is what turns a regular MLP into an RNN. Normally the user only cares about the inputs and the outputs. The hidden state is what gets passed through time in order to preserve some memory. Questions? Okay.
So here, hidden was like some function of the input.
Hidden is a vector. It's not a function. The only function you see is these functions defined here. These are the predict functions. Right? So hidden happens to be an extra vector we introduce to the situation. In addition to the input vector and the output vector, for each time step, I'm also carrying around the hidden vector. Yeah.
Is this type of architecture problem for many batches of something?
If your sequence lengths are not identical, they might be. We'll talk about that in a bit later. Okay? All right. So now that I have my unit of computation, how can I actually build models to solve the various sequence-related problems that I've mentioned before, such as sequence classification, sequence tagging, etc. So let's go over here and show you this picture. Yeah, so let's look at this picture. So the leftmost figure represents our MLP, right? I have a single input, single output. There's nothing going on, no memory. That's the MLP. Now, I can organize things this way. There's a single input in the beginning of time, which basically gets me started, and I generate many, many outputs. So this is a sequence generation problem. So I can give as examples image annotation. So this single input in image annotation is some sort of representation of the image, probably through a convolutional neural network model. You map this image to a large vector, and you use that vector as your initial input. And then the RNN generates words for you. Okay? And in that case, the words are represented as a big softmax over the whole vocabulary. Right? So each word, if you have 10,000 words in your vocabulary, then each output vector is a 10,000 dimensional output. And you softmax that and you compute probabilities for words. Here's another architecture that we can build out of this. So in this architecture, we're basically ignoring some of the inputs, right? So at time steps 2 and 3, we don't look at our input anymore. We just look at the hidden, or the inputs are 0. Here, we're ignoring some of the outputs, okay? In steps 1 and 2, we don't care about what the output y is. It doesn't affect our loss. We're only interested in the final output. what's an example of this? Sentiment analysis. So you read a whole piece of, Twitter text, and then you classify it as positive or negative, or IMDb movie review, and then you classify it as positive or negative. So the important classification comes at the end after you read the whole sequence. You don't know the size of the sequence, but your RNN doesn't care, it just reads every word and then remembers whatever it needs to remember inside its H vector, the hidden vector. And at the end, hopefully that hidden vector is going to have enough information in it to summarize this whole thing as positive or negative. This one is a sequence-to-sequence example. So the typical thing, typical applications are machine translation and speech recognition. In both machine translation and speech recognition, we have an input. In one case, it's a sentence made up of words. In the other case, it's an acoustic signal made up of, signal frequency, strengths, or what have you. And the output is a sequence of words as well. But crucially, the input size does not match the output size. Okay, so audio signals are sampled at a very high frequency, and there's a lot of input steps compared to the output in speech recognition. And in the case of machine translation, the languages are different, so the input-output words may not be equal. So in that case, I actually use an interesting architecture called sequence-to-sequence, which actually consists of two separate RNNs with two separate sets of weights. One is called the encoder RNN, the other one is called the decoder RNN. This picture doesn't actually make this very clear, so let me draw that for you. So here's the S2S model. So here's the encoder RNN. Let me mark that with an E. And the input sentence goes into that. And then the final hidden state, representing the whole sentence, goes into a different RNN as the initial hidden state. That's called as the decoder RNN. So we initialize that with a 0 input, and we get the first word. And we give it the first word as the input. It gives us the second word. And at some point it will give us end of sentence. So this is the sequence-to-sequence model. Okay, so two separate RNNs, not 6 separate RNNs, not every box is different, okay? So there is 2 different boxes. One, box E for encoder, the other one is box D as decoder. We just use them more than once. Okay? So X1, X2, X3 are the words of the English sentence, let's say we want to translate. And then Y1, Y2, Yn are the words of the Turkish sentence we want as an output. The encoder only reads its inputs and builds up a hidden vector. It doesn't actually generate any outputs. We just care about the hidden vector on the encoder side. The decoder actually takes the previous word and predicts the next word, also taking and outputting a hidden state. Any questions about this model? Yeah.
So when we're predicting bytes, their words,
Right.
well, then they have, like we construct a dictionary that's perhaps
Right.
consisting of 30,000 words.
Correct.
Then do we actually go ahead and calculate the softmax of it, 30,000?
The softmax function doesn't care. So your output is going to be 30,000 dimensional. And the loss, the NLL function, for example, is going to ask for the correct index from you and then calculate the loss, which is the minus log probability of the correct word in your vector.
Oh, I was actually wondering, maybe there is some, for computational efficiency, we
Yes.
some kind
So
of
that in machine translation models, you are right. In fact, the computational cost of that final softmax dominates the whole thing. And people have various tricks to try to reduce that computational cost. We might mention some later. There's certain approximations like NCE that make the training faster. There's hierarchical softmax, in which instead of generating one of 10,000 values, first you generate one of 100 classes, and then for each class you generate again one of 100 words, so you get to the 10,000 2 steps, and each step is relatively cheap. So there are various ways of addressing that issue. But in the simple models we're going to build, it's going to be just flat. Yes?
Are the horizontal arrows called H in our model?
Correct. And H is actually shared. The weights of the E encoder and the D decoder are separate. The W's are separate. But the H is passed from one to the other. Yes?
I might be wrong, but as far as I know, you don't have to condition the previous output in the decoder case. Just giving blank inputs can also create a.
I've never seen that done.
You have never seen
No.
that? Okay.
Both in language models and machine translation models, I know you always give the last word to predict the next word. You can probably generate something without doing that, but I've never seen that done. Okay. Yeah.
What determines the structure of H?
H is just a vector. It's your hidden vector. It's, you basically give it the size. I don't know, for machine translation models it's usually 1,000. For character-based models it's less. It basically, whatever your GPU memory allows is what determines the size of H, usually. One idea I can give is, in certain experiments I ran with the sequence-to-sequence model for a copying task, not a translation, but a copy. So you basically input an English sentence, and encoder maps the whole thing to a vector, and then you expect the decoder to generate the exact same sentence. So somehow the encoder, no matter how large this sentence is, must fit all the meaning of this sentence into a fixed size vector. Okay? So when I did that with English sentences of up to, I think, 40 or 60 words, I found that there was a limit, I think it was 700 or something, below which it couldn't memorize these sentences. And if you had more than 700 hidden units, then it was able to memorize these sentences. So it depends on how much information you want to store in this hidden vector.
Did it also perform good on test set?
Yeah, these are test set, of course, test set performances. We never look at the training set performance. Well, we sometimes do to diagnose what's wrong with the model, but okay. So next thing I want to talk about is backpropagation through time, which is basically how we train these guys. So in order to understand backpropagation through time, we need to understand this picture of unrolling the RNN over time. So here is one particular picture of an RNN. What does it tell us? xt comes at time t, goes into this box called A, which contains our weights and stuff. This box basically generates a hidden vector, and our output here, I call this yt, he calls it ht. And this hidden vector actually is fed back to the box itself. And then we get the next word, and then there's another cycle. So one way to see RNNs is basically, if we were actually to build an actual physical machine, a brain, connecting neurons together, what would make an RNN is this cycle, is this circular connection. The circular connection is allowing us to keep around some memory. H lives on that cycle. Okay. Now, however, when you look at this graph with a cycle, backpropagation becomes a little difficult. You know, how many times am I going to turn around that cycle and stuff? So in order to understand how we can use backpropagation to train this thing, we imagine this RNN to be unrolled in time. Now, I've been drawing things in this way since the beginning of class, so this is not very surprising to you probably. But know that the actual machine is not like this. The actual machine has a single A to which we keep following different XTs and getting different YTs. The actual machine looks like this. This is a picture that's been unrolled in time. So unrolling it in time has the advantage of making clear what the architecture is doing. But also, we can look at this graph and say, oh, this looks like one of those deep CNN models with layers and layers of stuff. And, while it's taking inputs and we're calculating losses at various levels, that's maybe the main difference. But other than that, if I actually took this and turned it 90 degrees, it would look like one of those deep CNN models. And I know how to take backpropagation, how to do backpropagation in these deep CNN models. So why don't I just do that? Right? So I'm going to calculate loss at every H and then propagate them through the whole network all the way from the last step all the way to the first step. And I have to be careful because all of these boxes share the same weights, right? So there's some weight sharing going on, just like we saw in convolutional networks. I can imagine these boxes to be separate. That's fine for drawing a picture, but we need to keep in mind that there is one set of weights. And that one set of weights is used multiple times. So that means during backpropagation, all these effects from the different losses and all the effects that the weights had at different time periods have to be taken into account. They have to be added up. Okay? So when I was first manually trying to train RNNs, this was a very scary picture. And to think about it and to write the derivatives without making a mistake was a bit difficult. I might, quiz you with a small example during the midterm maybe, just as torture. But after I wrote KNet, you don't have to think about that anymore. You just define your loss function, and all this backpropagating the gradients through time, etc., whatever, is automatically taken care of for you. Okay, this is where KNet and other automatic gradient systems actually shine. You just have to define the forward loss function. You have to define, so here's the one way to define it. So, so the RNN loss function takes parameter, some inputs, which is a sequence, okay, the initial hidden state, and some outputs, which is also a sequence. Now, what I'm going to do is I'm going to take these parameters and hit input t from 1 to n, basically simulating that picture, and accumulate loss. So how do I do that? I basically set my sum loss variable to 0 at first, and then for each time step, which is determined by length of inputs, for each time step, I run my RNN function. Remember, RNN takes a parameter, some input at time t, and the current hidden vector, and then it returns some output yt and the next hidden vector. Okay, so that's what this line is doing. And how do I calculate loss? Well, outputs t is the desired output that was given to me by the training set, and the output variable is my current prediction. So I compare those two and calculate some sort of loss, maybe a cross entropy loss or quadratic loss, whatever is appropriate, and I add that to sum loss. So all the losses at different time steps are added on top of each other, and then I return that. Okay? As long as you write a function like this, which basically seems like its only purpose is to calculate the loss of this model, then this magical grad takes care of the rest. You say grad, and you get a RNN grad function, which magically takes the exact same inputs, but returns to you the gradients with respect to parameters, taking care of all those additions and stuff. Okay? Yeah.
So if we want to do this for a sentiment analysis
Yes.
example, you don't have to sum the losses, right? You just look at the last
That's correct. In sentiment analysis, there is only one time step where we care about. Yeah.
Was there any mini batching here?
No. I'm going to delay talking about mini batching as long as possible because it's ugly. We'll see some code examples and then we can talk about mini batching. But I want you to understand everything else first, thinking of a single instance, a single sequence, and then we'll do another session on mini batching.
And all of this is for offline knowledge, right?
Offline meaning?
Like the whole data we have it, then we use it, train the models. Like where the data are coming one by one, maybe by some sequences.
You can apply the same thing to streaming data. That's true for, any of the models we've learned, right? So whether or not you have the whole data set right now, or it's coming out of some dynamic process, doesn't matter.
But when the new data comes, then we need to like have all of the data and train it one more time. But,
No. So let's say I'm training a machine translation system. You give me an English-Turkish sentence pair. I do this. I update my weights based on the gradient. You give me the next English-Turkish sentence pair. I do the same thing. I don't care how many of these you're going to give me. There can be an infinite number of them. After every sentence, I do a weight update. Yeah.
So let's assume we are not doing a machine translation class, but we are trying to predict stock prices.
Okay.
And we have so we determine the sequence length,
Right.
let's say 50, and
Why? What's the sequence length about?
because we unroll it to a certain.
During training.
Yes.
During testing, you don't need to determine a sequence length. During testing, you can basically just keep going with the same RNN
Yes, okay.
for an infinite number of steps. But during training, yes, if you don't want the gradients to go too far back in the sequence, thank you for bringing that up. If your sequence is too long, sometimes people do truncated BPTT. Remember, BPTT was back propagation through time, and now we're adding another T in the beginning, which is truncated, which means you have a sequence thousands and thousands of tokens long. If we actually try to do BPTT, we would have to go through the whole sequence and then call the grad function, which would basically accumulate gradients for the whole sequence, which might be inefficient. So what people do is they go 20 steps, do a backprop. They go another 20 steps, do a backprop. So even if the sequences are not naturally truncated like sentences, during training, people go in blocks to speed up the backpropagation through time. Is that?
Yes, and if we try to, we are trying to do, we are trying to update our weights as, we have a trained model, but we are also streaming new data.
Okay.
We have to wait, for example, 20 steps in order to update our weights, right? Well,
You can also update it every time. Looking back, 20 steps, it would be sort of, redundant. But there is nothing that holds you from updating every time step if you want. By always using the last 20 steps in the history, for example. Okay? Yeah.
In the previous examples, the hidden vectors were being proceeded to the next step.
That's correct.
But in this example, output
They
stems-
still are. They still are, right? So the output hidden gets written here and that gets used in the next step. So the hidden variable always points to the last hidden vector that was computed.
Okay, I mean the image. Image output hidden through output.
The image uses H where I would use Y.
Ah,
So just consider these things as Y. The arrows between are H. Okay, so
and,
that was.
okay.
Okay. Any other questions?
What is the first hidden state?
You usually set it to 0. That's one way. A 0 vector, I mean. Another way is you actually learn it. Your H0 becomes another parameter. Since you can actually calculate the gradients all the way back to H0, you can also update that and find the ideal initial hidden state to start with. Okay. All right. So now I'm going to talk about the most popular variant of RNNs called long short-term memory, and the best source explaining this is Ola's blog. So we're going to look at some of the pictures here, but first let me start with laying out the problem. Remember when we were talking about deep CNN models, how people invented inception modules, skip connections in residual networks, different mechanisms, and mostly they were trying to fight with passing the gradients back on a very long sequence of operations, right? Now, usually passing gradients back through a sequence of operations is difficult. I'll show you, I'll actually explain this to you in two ways. So let's call this section vanishing and exploding gradients. So my intuitive way of understanding is basically, you have a very long sequence of operations, and over here, you have the final operation, and over here, there's I'm drawing this like a long, weird creature. So basically, you have some weights at the tail end of the creature that you're jiggling, and you want to make this thing go moo or whatever, right? So that's the output. That's where the loss is determined, especially in the CNNs or sequence classification type examples. And you can imagine that since there's a lot of operations in between, moving one of these weights in the very beginning step by epsilon is going to get lost. Its effect on the, all the way at the end of the network is going to be lost in noise. Okay, so my typical picture is a very long cow. I'm tickling the tail of the cow, and it's not having any effect on the other end of the cow because it's just going through too many things. So that's my cartoon explanation. Here's a more mathematical explanation. So let's say I'm calculating the hidden layer of some regular 10H type RNN. So, and I'm going to ignore the input for now. Let's say I have no input, so I basically multiply only the hidden to get the next hidden. Okay, so there is a linear operation. I'm also ignoring biases, and there is a nonlinear 10H. And I can, the more layers I add, the more I actually repeat the same thing. W times another 10H, W times HT minus 2, HT minus 1. So let's think about what happens if we keep repeating this 10H W times operation over and over and over again. Do we get values that go out of control, or do we get values that vanish going forward? Vanish is one guess. Any other opinions?
Possibly both.
Possibly both. I'm going to say neither. And the reason is 10H. 10H doesn't care what the inputs are. It always maps everything to between -1 and 1. So that means going forward, my values are always going to be under control. They're never going to blow up to millions. I mean, they might die down to 0, but then the next, you might get another input that excites the whole thing. But basically, going forward, no matter how long the sequence is, I don't have problems with, underflow or overflow. However, going backward is a different. So this is the forward pass. Going backward is a different story. So the backward pass looks like this. going to use the right notation because I was warned before the class. So the derivative of the loss, the gradient of the loss with respect to ht, I'm going to, in the backward pass, I'm going to calculate that using the gradient with respect to ht plus 1. I'm moving backward. Somebody gives me the effect of ht plus 1 on the output. I need to calculate the effect of ht on the output. Okay? All agreed? So this is, if you actually do the calculus, you get W transpose times ht plus 1 gradient dot star element-wise multiplication with some f of ht plus 1. And this comes from the derivative of tan h. Okay, so this W transpose comes from the derivative of the multiplication, matrix multiplication. This comes from the derivative of tan h. It's, in case of tan h, it's going to be 1 plus ht plus 1 and 1 minus ht plus 1 multiplied together.
So what was the operation between the parentheses?
Dot star.
That's
I'm using the Julia notation for element-wise multiplication. All right, so now I start with some sort of gradient of j at the final layer, let's say, in a big T. I dot start with some vector whose elements are between -1 and 1. In this case, actually, they're always between 0 and 1 in the case of tan h. But this f is usually a well-behaved function. Okay? It generates vectors within well-behaved limits. So this multiplication is not going to hurt me. If the values I have here are nice, then after I do the dot star, they're still going to be nice. However, this multiplication gives me no such guarantee. In fact, when I go from ht to ht minus 1, I'm going to multiply with the exact same matrix again, because this is my one and only weight matrix. And every time I go from t plus 1 to t minus 1 to t minus 2, I have another multiplication of my gradients with the exact same matrix. So what happens when you start with some sort of vector and keep multiplying with the exact same matrix? Anybody know?
Explodes or diminish to zero.
Why?
If it's bigger than 1.
What's bigger than
for,
1?
For a scalar, if it's a bigger than 1.
Eigenvalues.
Right, so for a scalar, if I'm multiplying the same number with a scalar, if this scalar is bigger than 1, eventually it'll explode. If it's smaller than 1, it's going to shrink to 0. However, what's the equivalent of that in matrices? Eigenvalues, right. So the way to see that is basically any matrix, like any WT matrix, can be written in terms of its eigen decomposition. So this is the eigen. So V is a matrix of eigenvectors. This lambda, big lambda, is a diagonal of eigenvalues. And if you keep multiplying with this thing over and over again, what's going to happen? Well, the V inverses are going to cancel the V's. Okay, so WT to the power n is going to leave a V in the beginning. This guy is going to be raised to the nth power. And there's going to be a V minus 1 at the end. And here lies the problem. Okay? So this is a diagonal matrix of eigenvalues. And raising it to the nth power means every number in that matrix gets raised to the nth power. Every eigenvalue gets raised to the nth power. So any eigenvector that had an eigenvalue above 1 is going to now have a diagonal entry that approaches infinity. Any eigenvector that has an eigenvalue below 1 is going to get a coefficient that's close to 0. Okay? Now, my initial starting vector can be decomposed into these eigenvectors, right? So the components of this initial gradient vector that lie along the eigenvectors with larger than 1 eigenvalue are going to explode, and the components that are lower than 1 are going to shrink to 0. So that's the vanishing and exploding gradients problem. Okay? So in order to solve this problem, as we saw, convolutional neural networks invented all these skip connections and different architectures. RNNs are no different. These are actually older than the convolutional case. In 90s, they invented this thing called the LSTM, which looks ugly and which takes a bit to understand. But the reason we still use them is nobody has been able to do something significantly better. This module actually works really well with keeping memory in long sequences and being able to train. So we already saw these pictures. Let me get to the LSTM. So here's a standard RNN. Okay, we can see it like a train, the same module repeating over and over again. It's inputs xt minus 1, xt, xt plus 1. And what happens? Well, there's an arrow coming from the top. That's your hidden vector. And xt is coming from the bottom. They get concatenated, right? And multiplied through some w, sent through a 10h. And the output of 10h is basically your next hidden vector, which in the case of this figure is used both as output and hidden. Okay. So, and the linear multiplication was the problem. So LSTMs do this very complicated looking thing. Okay. So they're a bit more involved. There's like 4 different operations. So there's some element-wise multiplications and additions. And everything will be clear, hopefully, in the next 5 minutes, why we do these things. So first of all, let's understand what these things are. So let's agree on this. So boxes are neural network layers. This is a point-wise operation. Vectors move through these arrows. When 2 arrows get together, you're concatenating the vectors. And when an arrow splits into 2, that means you're copying the same vector to 2 different places. Okay? So now let's look at this picture again. With certain parts shaded out. So the main thing that carries information from past to future in an LSTM is this upper thing called the cell value. Okay? LSTMs actually have 2 hidden vectors. One is called the cell, one is called the hidden. Cell is the CT and hidden is the HT in this picture. So the cell value enters from the left and then gets multiplied element-wise by some numbers between 0 and 1. Okay? So that basically, this multiplication determines which of these cell values do I want to forget, which of them do I want to keep remembering. Okay? So whatever you want to forget, you multiply it with a number close to 0. Whatever you want to remember, you multiply with a number close to 1. That's the purpose of this operation. And then over here, whatever new value I computed from my current input, xt, I'm going to add to this cell. So in this operation, I forgot some of the old things. In this operation, I added some new things to my cell, both element-wise operations, and then that basically gives me the next value of cell. Okay. Now, this all sort of commonsensically makes sense. We forget certain things, certain dimensions of this vector, and then we add other things from the current input. But the important thing is there is no matrix multiplication, which was the problem that we had before, that actually led to the exploding or vanishing gradients. If cell is the important thing that carries information from the past to the future, the gradients along this path are not going to vanish or explode because there is no matrix multiplication. There is just a scalar multiplication with some numbers between 0 and 1, and there is some additions of some numbers between -1 and 1, neither of which is going to make you very rich or very poor. Okay? You're not going to explode or vanish. Yeah.
Cell is something like H?
Yeah. So we have 2 hidden vectors. One is called a cell, one is called a hidden. Okay, so let's look at the details of where these numbers are coming from. So I mentioned that we want to forget certain things, and in order to forget certain things, we element-wise multiply a vector with another vector of the same size that has numbers between 0 and 1. Anything multiplied with 0 gets forgotten, anything multiplied with 1 gets remembered. Now, how do you convert an arbitrary vector into a vector of numbers between 0 and 1? Using the sigmoid function. So this is the sigmoid function. So whatever is here being computed gets passed through a sigmoid function, which converts it into numbers between 0 and 1, and then you multiply that as the forget operation. Okay? This is actually called the forget gate. So here is the full description of the forget gate. So, as everything else in RNN, the forget gate is a function of the previous hidden state, hidden vector, and the current input. Okay, so that didn't change. Remember, in the simple RNN, our inputs were the hidden vector and the current input. It's still the same. The inputs are the hidden and the current input. We basically calculate some sort of linear function of these things, which is another vector of the same size, same hidden size, pass it through the sigmoid. That becomes the vector ft, which is our forget vector, and we use ft to forget certain things. Any questions about the forget gate? This is called a gate, sort of electrical engineering.
Always functional t minus 1 here?
Say it again?
T minus 1, is it functional always t minus 1, or do we use like t minus 2 or?
Only the function of t minus 1. There you can actually come up with architectures which connect to earlier points in time. There is nothing holding you from doing that. In fact, that's something that I do want to experiment with, because in the last lecture when I was talking about CNN architectures, one of the tricks the ResNet did is basically skip connections, right? So this solution does not use any skip connections. So maybe one of you can figure out a way, instead of doing this monstrosity, maybe adding some skip connections to a simple RNN would work just as well. So that's, I think, a good idea to try. Okay. Now there is a bunch of other gates. Remember, we want to also add new information to our cell. Here is the way we add new information to our cell. So first of all, again, as a function of ht minus 1 and xt, we calculate some candidate new information. This is the CT tilde. So let's call that the new cell. Okay, this is the new cell content that I want to add. Okay? And that's computed as, again, ht minus 1 xt, multiply some linear transformation, pass through tan h. So all the numbers are nice between minus 1 and 1. So I now have a same size vector that I want to add on top of my existing cell. However, before I add that, I do another trick here where there is this type of gate that suppresses some of these new values. Remember, I suppress some of the old values using the forget gate, and I suppress some of the new values using what's called the input gate, IT. So I calculate some new values from these guys, and then I suppress some of them using the same gate functionality. Okay? And then after the suppressions, after CT minus 1 is suppressed and this new cell is suppressed, I basically add them together to get the new cell value. Okay, so here is the suppression. So, and this actually summarizes it well. This is the new information, this is the old information. FT forgets some of the old information, IT forgets some of the new information, and then I add them up, they become my new cell content. Okay, this is the main output of the LSTM. And finally, I need to calculate another hidden H, and I do that using what's called the output gate. The output gate is similarly calculated from the cell value. The cell value goes through a tan H and then gets suppressed using this output gate and the result becomes HT, which is the thing that goes to the next, which is another thing that goes to the next time step. Okay, as you can see, this is quite involved and seems unnecessarily complicated, but people have done experiments with trying tens of thousands of random architectures, and so far they haven't found anything that does significantly better than LSTM. There are some simpler alternatives. A new one is called, not so new anymore, a GRU, for example, gated recurrent unit. I think this is one people connections. There's variants of this thing. So here's an idea. I don't know if anybody uses this, but if I'm going to suppress some of the old information and suppress some of the new information, shouldn't these things be complementary? Right? So I should either suppress one or the other, given a dimension, where, but the regular LSTM is deciding independently which ones to suppress. So here is an idea where the suppression vector is only computed once. There's only one forget vector, and it's applied to the old input, and its negative is applied to the new input, or not negative, but 1 minus those values are. So basically, the new cell value is always some number times the old value, and 1 minus that number times the new value. And here's another alternative called GRU, which is also used frequently. It has a slightly different structure, but same type of idea. And the whole thing is basically, the big point is the information carrying path up top does not have any matrix multiplication, so it doesn't suffer from the diminishing gradients or exploding gradients as much. Okay. Any questions about these before I show you some examples?
Are these prone to overfitting? Or?
They're no different than any other learning algorithm that we've studied so far. Yeah.
So you mentioned they tried like 1,000 experiments or so to optimize this LSTM, but I'm still having a hard time to why this is working the best. Like, is there any other explanation?
This is the best I was able to find. So number one, it basically solves the vanishing and exploding gradient problem by not having matrix multiplications in the upper rail. So that's the important thing. And then number two, the basic idea is you're carrying some information forward, that's your memory. And at each time step you want to forget certain things and add certain things. And what you want to forget and what you want to add should be a function of the current input. Maybe the current input is very important, so you want to forget everything else and just remember the current input. Maybe it's something that you can ignore. In that case, you want to carry the old information forward. Okay. Instead of showing you examples, I'm going to briefly talk about mini batching, since you guys asked it 5 times and it's important. So usually the input to an RNN is a sequence. So let's say this is one of the sequences. So x1 through xt, and I want to mini batch in order to train faster. So I have another sequence here, another sequence here. So these are all sequences. So mini batch size B is 3. I have a mini batch of 3 sequences here. Okay, and each of them are of length. The time goes 5 steps. Okay. So now, if I have a mini batch sequence like this, how can I feed this to an RNN? Well, I can take the first vectors in each sequence. These are representing the first words of each sentence, let's say. So So let's say this is the first word of the first sentence, S1, 1. And I take the first word of the next sentence, S2, 1, S3, 1. Okay, so these are vectors representing these words. I put them all together into a matrix, and I can basically do the exact same operations because there's going to be a W multiplying them, etc. This is just like regular mini batching. Okay? And after all these operations, what I'm going to get is a Y vector, an output matrix, and an H matrix, and sometimes if I'm actually working with an LSTM, also a C matrix, each of which will have B columns, right? So because I started with B different parallel inputs, so I'm going to have B columns in each of these vectors, and you know the height depends on the dimensionality of the output and the hidden vectors. So these each actually have B independent operations going on in them. Okay? So what do? I feed the first words to the RNN. I get my output and my hidden vectors in parallel for the next step. So I use these things as with B matrices again, and take the next words from each sentence and feed that, and take the next words from each sentence, feed that, and I can basically run through the whole sequence in parallel, whole set of sequences in parallel. Any questions so far? Yeah.
But if the first sentences don't have the same number of tokens?
Okay, I'm going to talk about that next. Any other questions? Okay, so the problem is, what if the sentences don't have the same length? So what if the first one is longer, and the second one is shorter, third one is whatever, right? So here we have a problem because after I come to this word, you know, some of my words are missing. How am I going to construct the next mini batch? Right? So there is at least 2 or 3 different solutions we can think of for different sized sequences. We can do padding, we can do masking. In addition to these, we can do sorting, so this actually occurs less. And I'm going to talk about RNN form at some point. Let me put these things first. Okay, so padding means take your longest sequence and add some dummy tokens to the other sequences so that they're all the same length. Okay? So you basically designate a new token called the dummy token, and you add as many dummy tokens as necessary to make all sequences the same length. Okay? So that's padding. It's the simplest way to deal with this problem. And it works fine usually. Yeah.
Just asking for curiosity, like how a dummy words looks like.
Every word looks like a word vector.
Yes. And
So your dummy word will look like a vector too.
what is inside?
Numbers.
Dummy numbers.
Dummy numbers. Well, every word starts with some random numbers, so your dummy word also will start with some random numbers. And then it will get trained during training, just like every other vector. Okay? Any other questions? Now, the problem with padding that I don't like is that it changes the objective function, it changes the problem. So in other words, if you actually train the same network with batch size equals 1, in which case there's no padding characters, you would learn a different set of weights. If you use different batch sizes, the number of padding characters will change and you will learn a different model. So that if this difference is bugging you, like it used to bug me, then the next idea is masking. So masking is the following idea. For example, when I'm passing this thing as a vector, as a matrix to my RNN, I also pass a mask vector indicating which ones are real values and which ones are padded values. Okay? So for this time step, for example, the first is a real value, the other ones are fake values. And for the previous step, for this step, the first and the last ones are real values, the middle one is a fake value, for example. Okay? So let's say in addition to every X matrix that I pass, I also pass a bunch of ones and zeros that tell the RNN that some of these values are fake. Okay? So how can I use that to avoid the padding tokens having an effect on my calculations? Right, so going forward, for example, you can multiply where, you know, all the downstream values from these fake tokens with this mask. So they will get multiplied with 0, they will have no effect on the output, therefore when you're going back, the output gradient will have no effect due to these padded values. So you basically want to erase everything that was done using your padded word vector. And you can use the mask to accomplish that. It's not that difficult, but it's slightly more complicated than just adding another token to your vocabulary. Sorting, so if you have a bunch of different sentences of different lengths, you might want to actually sort them by length before you start training, so that it's more likely to get a whole bunch of length 5 sentences together, a whole bunch of length 6 sentences together, instead of starting randomly. Now, if you do that, one thing to pay attention to is do not start training with the very short sentences and go toward the long sentences, because then in the beginning of the training, your network is going to learn to process only short sentences, which will make it, you know, push it into a region of space you probably don't want. So instead, what I recommend is sort, mini batch, and then shuffle the mini batches and feed them to the network in a random order. So this way, each mini batch is relatively the same length sequences, but the consecutive mini batches don't always come short, short, short. They are mixed in size. Yes?
You still got to use padding and masking here, right?
Yes, but less,
Yes.
because you know the number of pads you need to use become much less, so it becomes more. This is actually a speed trick in that sense. It makes it faster if you have less pad characters that you lose time on, because even though you're masking them with zeros, you are doing all those multiplications, and the less pad characters you have, the better. Yeah.
Can we also use varying batch size for this sorting? For example, if the sentence length 5 and there are 3 of them and 5 from the 40 length of them.
Varying batch sizes. So you want, yeah, so if for a certain length you don't have as many examples, you want to use maybe a mini batch that's slightly less size. Yes, you can. It might lead to some inefficiencies because new size memory arrays need to be allocated and stuff. But yes, that can be done. And so the final thing is RNN forward, which is a function implemented in whodnn actually that we imported to KNet. That also has its own solution to this masking and padding problem done behind the scenes, so we'll talk about that next time.